Hello there guys, and welcome back to another epic inexorable maths video. In this video we're going to prove a result about Laplace transforms, namely the Laplace transform of the nth derivative of f of t is given by this formula. So it's s to the n times f of s minus s to the n minus 1 times the function evaluated at 0 minus s to the n minus 2 times the derivative of the function at 0, all the way down until we get to finally minus the n minus 1th derivative of the original function evaluated at 0, which you can also write using sigma notation as the following. I won't read it out, but there it is. It's not very nice in sigma notation, but it follows a pattern that you can see quite easily. So let's just, for example, do some, right? So we can see that, we already know this, but the Laplace transform of the first derivative of f of t, just according to this, is just going to be s to the power of 1, because it's the first derivative. So s to the 1, which is just s, times capital f of s. And then notice, though, guys, that if n is 1, then this is just the sum from I equals 0 to, well, 0. So it's just substituting 0 into this. So we have s minus s to the power of, well, n minus 1 minus, well, I is just 0. So, and n is 1. So it's 1 minus 1 minus 0. So it's just s to the 0, which is the number 1. And then the 0th derivative evaluated at 0. The 0th derivative is the original function, of course, so it's just evaluating at 0. Now, we already knew that this was true because we've proved it in the previous video about Laplace transforms. So this is fine. It proves that it works, right? Here's one more. The second derivative's Laplace transform, which I won't write as f double prime, I'll write it as f2 in little brackets of t. And that's going to be equal to, again, let's do this. So s to the power of 2 this time times capital F of s minus, and now we want the sum from I equals 0 to 1, because it's to 1 less than the power. That's the sum to n minus 1. So we evaluate this at 0, and then we evaluate it at 1. So evaluating at 0 of these brackets here, we've got s to the power of 2 minus 1 minus 0, so 1, times the 0th derivative, so f of 0. And then evaluating at 1, we have s to the power of 2 minus 1 minus 1, so s to the power of 0, times the first derivative evaluated at 0, like that. So we can kind of see a pattern here, right? The power of s is just going up, corresponding to the order of the derivative. So if it's the first derivative, it's s to the 1. If it's the second, it's s to the 2, etc. And then what you're doing is you're kind of descending the power of s and ascending the derivative, if that makes sense. So you're kind of taking the 0th derivative and then the first. For example, without even using the formula, the third derivative, what would that be? What would the third derivative be? Well, that's just going to be s cubed f of s minus s squared f of 0 minus s times the first derivative at 0 minus the second derivative at 0. So I've just done that from knowing the pattern, right? I didn't really use this. I'm just doing it from the pattern. So that's the pattern. You can do this. You can try it for yourself. But we want to prove it. So this is not difficult to prove. You can use integration by parts and just repeatedly do that. That's fine. But in this video, because I think it's quite interesting how you go about doing this, we're going to do it by induction, because induction is just quite cool and it's really, really nice in this question. So let's do it by induction right now. So the base case for our proof by induction is we want to prove this is true when n is the number 1. So we've already said just a moment ago what the Laplace transform of the first derivative is, but according to this formula, again substituting in, it's s to the 1 times capital F of s minus lowercase f evaluated at 0, right? Now that's what this formula is saying. But from the previous video, and again the link will be in the description as always, from the previous video on Laplace transforms, we actually worked this out without using the formula. We just did it using integration by parts. So we know that this is true. It's true. So I'll even write that this is the Laplace transform of the first derivative of f of t. We know that this is true, so it holds. So we can say that the statement, which is the original, it's this whole formula, the statement holds for when n is 1. Lovely. Okay, the next step, as always in a proof by induction, is the assumption step. The assumption is quite straightforward. It's just assuming that for some arbitrary k, so I'll write this down, so for some k, so when n is equal to k, and k is a natural number, so 1, 2, 3, 4, 5, etc., when it's one of those, then we are assuming that this equation is true. And I'm going to write it out in the long form way. I'm not going to use the sigma notation. You'll see why in a second. So for this, we've got that the Laplace transform of the kth derivative of f of t is just, and I'm literally going to copy out this very top line, but I'm going to replace the n's with k's. So it's s to the k times capital f of s minus s to the k minus 1 times lowercase f of 0 minus s to the k minus 2, first derivative at 0, dot, 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 all the way until we finally get down to the last term, which is the k minus 1th derivative of f evaluated at 0. Okay, so this is what we're assuming is true. I should have written that really. Assume that this holds, okay? Assume that this holds. That's our assumption. We're also going to quickly jot something down. It's not an assumption. It's just a quick note that we're going to need later on. So I'm going to write also, I'm going to introduce some new function which I will call g of t. So I'm going to let g of t be equal to the kth derivative of f of t, okay? Also, just a notation thing, I'm going to say that the Laplace transform of g of t will be denoted by capital G of s, which is no surprise at all, because the Laplace transform of lowercase f of t is capital F of s. So this is completely not a shocker at all, right? G of t is going to have a Laplace transform, and we're just going to call it G of s. That's it. These two things are not assumptions. We're not like assuming that they're true. They're just things that I've written down. They're completely valid. It's just saying that your function G of t will just be the kth derivative of f of t. That's all we're saying. Lovely. Okay. Now for the fun bit. This is the induction, or the inductive hypothesis. This is the cool bit. Okay, so what are we going to do here? Well, here we want to see what happens when n is k plus 1. What the whole kind of idea of a proof by induction really is you're trying to show that if the statement holds for when n is k, it will also hold for when n is k plus 1. And because we've already shown that it holds for 1, if it holds for some arbitrary k and it holds for k plus 1, it actually must hold for all natural numbers, which is very powerful. But what we want to really do is show that when n is k plus 1, our kind of formula for the Laplace transform of the k plus 1th derivative of f of t looks identical to our assumption, just with the k's being replaced now by k plus 1s. okay? So we basically want to get that the Laplace transform of the k plus 1th derivative of f of t is given by this exact formula, but the k's need to be k plus 1s, okay? So basically just increase all of these powers by 1, if that makes sense. We need to make it look like that. So how are we going to do that? Well, it's difficult because you can't just substitute it in, of course, because you're allowed to assume that it holds for k, but you can't assume it holds for k plus 1. That would be not very good at all. So how are we going to do it? Well, this is the key to why we've introduced this g of t situation. This is, in my opinion, really clever, and this is why I wanted to do this proof with induction, because when I was researching for this video to see how you would actually do it with induction, because I didn't know, to be completely transparent, I don't just know these things, I researched, of course, I was absolutely blown away by how cool this is. So I hope you guys appreciate this as much as I did. So if you want the Laplace transform of the k plus 1th derivative of f of t, why don't we take g of t and the kth derivative of f of t and differentiate both sides of that equation? So if g of t is the kth derivative of f of t, then the first derivative of g of t is, of course, the k plus 1th derivative of f of t, right? So I'm just taking this equation here and I'm differentiating both sides once, and I'm getting this, okay? So now let's take Laplace transforms of both sides here, because of course if two functions are equal, then their Laplace transforms are equal as well. So now we're going to take the Laplace transform of the k plus 1th derivative of f of t, which, as we can see, is also equal to the Laplace transform of the first derivative of g of t. Now this is the cool thing. G prime of t can be expressed as s times capital G of s minus g of 0, because this is a first derivative, and we've already proven it holds for n equals 1. So this is the Laplace transform of basically the first derivative of a function. And it holds, right? Of course it does. We've proven it already. So we know that this is definitely true. And again, this is why I've introduced this g of s notation. It's just the Laplace transform of g of t. That's all it is. Okay, now I think this is really cool. It's it's just cool, right? So now what we can do is we need to know what g of s is, right? Well, what's g of s? Well, g of s is the Laplace transform of g of t. Okay, well, what's g of t? Aha, it's the kth derivative of f of t. So g of s is the Laplace transform of the kth derivative of f of t. So I'm going to start this on a new line. The Laplace transform of the k plus 1th derivative of f of t is s times g of s, and again g of s is the Laplace transform of the kth derivative of f of t. So it's just s to the k as per our assumption times capital F of s minus s to the k minus 1 f of 0 minus s to the k minus 2 f prime of 0, all the way down until we get to the k minus 1th derivative at 0. Close bracket. And finally, we need g of 0. Well, what's g of 0? Well, again, guys, g of t is just the kth derivative of f of t. So g of 0 is the kth derivative of f of t evaluated just at 0. We're just letting t equal 0 in this equation here. So instead of taking away g of 0, we just take away the kth derivative of f of t evaluated at 0. And then this s that's on the outside gives us that extra 1 that needs to be in the power that's going to bring all these k's up by a factor of 1. So we get s now to the k plus 1 f of s as we expand, minus s to the k lowercase f of 0 minus s to the k minus 1, first derivative at 0, all the way down to the kth derivative at 0, oh sorry, not the kth derivative, s times the k minus 1th derivative, my mistake, and then minus the kth derivative evaluated at 0, like that. And I'll just move out of the way so you can see that. That's it. And that really is it. Because again, this is the Laplace transform of k plus 1, or the k plus 1th derivative of f of t. So notice that this last line here is identical to our assumption, except the k's have been now replaced by k plus 1s. So every single value of k that was in our assumption is now a k plus 1, as you can see. And what that means, I won't write it down, but what it means is if it holds for k, it must also hold for k plus 1. And because it holds for the number 1, it must hold for every natural number. And that's the proof. So that's basically the proof of this very top line. And I think that's really awesome. Thank you guys so much for watching. I highly appreciate it. As always, I'll see you in the next video.